So some might call this the max rule. I'm going to call it as follows. So this is the next property we're going to talk about here. Like I said, some people call this the max rule. Take the largest function over functions in a sum. So what do I mean by this? So given any two complexity functions, and I must stress that the statement is rather general. So functions f and g, then we can say that f plus g is big O of the max of f and g. So I'll explain what I mean by this in a moment here. So f plus g is big O of the max. That M is looking a little excited there. The max of f and g. So what does this mean? So if you're not familiar with the max function, the way this works is that if I give you some value for this function here, if ever I have some input of a sufficient value, so if I plug in a value like say 1 or 2 or 3 or 4 or 5, it'll take whatever the largest is of the values among them. So very often the way this max function would get used in this context is that if, say for example, f is n and g is n squared, then this means that all of this will be n squared. So it collapses into that. So you might ask, Dan, why would I want to care about this property? Now, very often when we analyze algorithms, not always, most certainly there's more delicate cases you have to be considerate of, is very often you have kind of parts to your algorithm. Say you have like the first part. I give an example kind of like this. You have the first part, the second part, and the third part. And say you know that the first part is something like, I don't know, like n. Say the second part is n squared plus 2 or something, many operations. And say the third part is, I don't know, actually we'll stick with just 2 for now. I'll make a remark about multiple ones. So say if I have 2 of them here, keep in mind you can always group them too. Say if I have 2 parts to my algorithm, the first part does some linear number of operations, the second part does some quadratic number of operations. What this rule is saying to you, this max rule, is saying to you is that if you take the sum of these, so suppose that these are the total number of operations that happen in your algorithm, for example, it doesn't have to mean that, then what it's saying is you take the max of f and g and you get that in terms of big O. So in this case, notice that you have n squared plus 2, so you could just simply say that this sum over all of these is big O of n squared plus 2, which more simply is big O of n squared. Okay? So this is what we're going to prove here next. So ultimately what I'm saying is that if you take the largest function over a sum of 2, then you're going to have it where you're going to end up with the largest one at the end for the big O. So we use this all the time when we count up operations in big O. When we're computing the big O for an algorithm when it has multiple parts. So what we do is we do what we usually do. So keep in mind you can say arbitrary complexity functions, but here I'm just going to cut right to the chase. So suppose that we have 2 arbitrary complexity functions, f and g. I'm just going to cut right to the chase, just to be clear. We find c and n0. Which remember, that's a positive real number. This is a positive integer. Such that for all n greater or equal to n0, we know that f of n plus g of n is less than or equal to c times the maximum of f of n and g of n. So what I'm saying here is that if I take the sum of these, it has to be less than or equal to c times whatever the larger of these two values will be for a given value of n. So anyways, you might ask, Dan, how are we going to pick the constant? And that's a very natural question, right? Well, I like to think of it in the following way. So let's think about this. Suppose that I had one function from this box, and I have another function from this box. And I want to claim that if, say, whichever of the two functions I take is big O of the max of the two, it doesn't really matter a whole lot if one function is much smaller than another for a given value of f. We could just take whatever's the bigger of the two, right? But here's the thing. That's what this says, right? So this is saying that I have f plus g. Now imagine that f is less than g. Then you know that this is going to be less than, like this sum is going to be less than or even less than or equal to g of n plus g of n, if that's the case. And you can think of the other case too, where g is less than f for certain values of, well, for sufficiently large value of n. Then you could say the exact same thing just in reverse, right? So you could say that, okay, well, that means that f of n plus g of n is less than or equal to f of n plus f of n, right? The point here is that there's two of them. So all I'm doing is summing over two, but each one always gets to be the bigger of the two. So a very natural selection for C will be 2. Why? Because I'm summing over two things and I'm always taking the larger of the two things. That's the intuition here. But we need to actually check that. Just saying that it seems right isn't enough. We need to actually verify this. Then we find n0, so that for all n greater or equal to n0, we know that f of n plus g of n is less than or equal to 2 times the max of f of n and g of n. Well, like I said, we can always fudge around with an f and g are by just simply taking the larger of the two. So I'm going to take our bucketing approach and I'm just going to extend that to just this case. So watch this. Well, for all n greater or equal to 1, both of the following inequalities are going to be true. Both f of n is less than or equal to the max of f of n and g of n, right? This has to be true, right? Because f is included in that max function. So if g ends up being bigger than f for values of n, where n is greater or equal to 1, it'll pick g. But if it's bigger for f, it'll pick f. So you're covering your bases when you say something like this. And g of n, for n is greater or equal to 1, that's important, is less than or equal to the max of f of n and g of n. Same reasoning here. So all I'm going to do now is I'm going to sum over these two inequalities. So I want something that looks like f of n plus g of n. Here's f of n on the left-hand side, and I have g of n on the left-hand side. So if I sum these two inequalities, I should get something that's very nice for us. So let's head on over here. Let me just take a little walk. Take it on, walk, walk, walk. And let's head on over here. So that's exactly what we're going to do. So for every n greater or equal to 1, we know that f of n plus g of n. So if you really want to get more precise about where this comes from, you can just point at those two inequalities. So this is something that you can do, is you can always make, like, put a star beside that inequality, and this inequality put like 2 stars or something beside it, just to indicate what they are. So for every n greater or equal to 1, by summing star and 2 star, you get this. But I think that it should be nice and flow from this way as well. Is less than or equal to the max And that's my curly braces are sort of a little sad, but that's okay. They're my friends too. Plus the max of f of n, g of n. So remember, this is what it says on that first inequality. F of n is less than or equal to the max of this. G of n is less than or equal to the max of this, right? That's what we said just a moment ago. But what's this? It's just 2 times the max of f of n, g of n, right? Which is exactly the right-hand side. There's nothing arbitrary about this if you just understand this bucketing approach we keep using. It's a feature. It's very nice. So I'm just going to make this a comma. So I'm going to choose n0 to be 1. Because this inequality works for all n greater or equal to 1. So now I'm just going to conclude our proof by invoking the definition of big O, and then we're done. Therefore, by the definition of big O, it has to be that f plus g is big O of the max of the 2. And we're done. I'm going to put a end of proof mark right there, and we're good to go. But yeah, no, so this is how you can prove this claim. This is one way to do it. One thing I do want to make a remark about this is that in a previous session, we talked about how we had this property that we have for polynomials. And you know how I talked about, oh, you just sum up the coefficients of the polynomial using absolute values on each one. And I gave you a proof for this. Now, you might find it interesting that actually you can generalize the max rule that I have here so that you have d complexity functions, and you're allowed to have it so that each complexity function has its own coefficient. And you can actually adapt a technique very similar to the one that you talked about when we talked about polynomials there. So if you have the max rule, it's like say if you have this max rule in place and you wanted to put coefficients on f and g, you'll notice very quickly that the way I picked the constants depended on the number of terms. So do you see that if suppose, for example, I have 3 terms or 4 terms or 5 terms, I could just simply pick the constant to be whatever how many terms there are. Likewise, I could introduce coefficients to each one of the functions and change them to those, and you'll see very quickly, if we use this max rule appropriately over d complexity functions, that you can actually generalize this rule so it subsumes the max rule and also the polynomial, the way you can handle a polynomial that I talked about previously. So I'll have that property discussed in the notes, but I'll write it here, okay? So I'm going to write it here just for the sake of completeness, but the proof will be in the notes. So here's a generalization that you can take to go even further than this. A generalization. So given d, which has to be a positive integer, it can't be 0 or negative for some reason. I don't know what that would make sense of being. Suppose I have some positive integer number complexity function, so d is a constant here. So what I'm claiming is that if you have d of these, suppose I give them names, f0 of n, f1 of n. So keep in mind, I'm just writing I'm saying the of for you to understand what I'm writing. And this goes up to fd of, so d minus 1 of n, and you have coefficients. And coefficients a0, a1, all the way up to a d minus 1, which is going to be, these are all going to be real numbers. What you could do is you could actually prove the following. And this is the generalization of both the polynomial case and also the max rule. So it's actually the combination of both, and it actually takes techniques from both of these. So if I have sum from I is equal to 0 to d minus 1 of ai times fi of n. So if I sum over all of these coefficients multiplied by each complexity function, it has to be that this is big O of the max, where you consider the max over all the complexity functions. So this is a generalization of the max rule over here. So if you make all the coefficients just 1, you'll see very quickly that it's just the same idea we had over here, just when you have it when d is equal to 2, right? So also, you'll notice that it should give you shades of the polynomial type of setup, is where you have d is equal to, I believe it's k plus 1, if I'm thinking offhand here. And then you just simply assign each function to be n to the I for some value of I in this sum.